Thanks for attending this talk. I will present recent work on OpenCL and Clang. I will mainly talk about the new standard we are developing, which is OpenCL 2.0. But I will also introduce OpenCL in general and also talk a little bit about OpenCL and Clang. The agenda of my talk is as follows. I will start from introduction into OpenCL, just to make sure that all of you can follow the rest of my presentation. And then I will talk about OpenCL and Clang, and the main focus will be, of course, OpenCL 2.0 and its implementation in Clang. If you have ever attended any presentation of GPU, this kind of picture might be familiar to you. But I just would like to introduce the programming model that we are using and terminology as well, as it will be important in the rest of the presentation. So we have, in OpenCL, we have host side. That's where host is basically just CPU. And that's where we create an application. That's where we cross-compile for device. We send work from host to device, and we copy data between host and device memory. Device is represented or is seen as a collection of concurrent execution items or work. And each unit of work we call work item. And it can access private memory to store data. It can be register or and a collection of this unit is this work items form work groups. And within work group, work items can access local memory, and all work items in all work groups can access global memory at the end. So the programming paradigm for host is just C or C++ and OpenCL API. And on the device side, we use OpenCL language to program. The rest of the talk, I will focus on OpenCL language itself and its support in the compiler. The core part of OpenCL language is still C99. And we have, of course, an addition to it that is represented with with additional keywords and constructs that we are adding. One of the key things is to specify parallel unit of work, which we call kernels. Something very different with respect to C, or in comparison to C, is that in OpenCL, when we declare objects, we have to think about where in memory they are located, and we actually have to bind all objects we declare to some memory regions. And as you have seen from this picture, we have quite a complex memory hierarchy. And programmers actually have to think about this memory hierarchy while writing the code. In order to bind objects to memory, we use address space qualifiers. We have some special types, for example, images, event, or pipes. And there is such thing as access qualifiers where you can specify for some objects whether they are being read or written or both at the same time. And then there is this gray part, small gray part there is what we basically disallow from standard C, or we modify semantic of it. For example, standard C includes all libraries are not supported in OpenCL. Instead, we have our own libraries. So if we think of writing a compiler for OpenCL, we would probably start from some picture like this there. We have classical compiler component, front end, back end, and intermediate representation being an interface between these components. And we would see it as extension to front end. So basically, if we want to compile OpenCL now, we need to build an additional layer in the front end that would be able to understand new constructs of OpenCL. However, in reality, things are a bit more complex and a little bit different. For example, on a front end, we have target-specific bits, and C is compiled for many different targets. Obviously, all these program paths that are target-specific are not valid for OpenCL, and the same happens vice versa. In OpenCL, we support targets that are not supported with just C. Something else we have is a conflict between C and OpenCL, unforeseen in spec, and that happens especially where we have undefined behavior. So compiler can decide how to implement certain thing, and then we have situation that in OpenCL something is forbidden or disallowed, and C compiler implemented some other feature that is making use of forbidden behavior. Another very important problem we have to deal with is how to generate IR from the front end such that it fits need of different architectures. And the problem we have here that a lot of backends and architectures for such kind of programming models are closed source. So a lot of companies are protecting their IP with regards to GPU architectures, and we don't have access to this information. So we basically have to think how to generate it such that we can fit the needs of all different architectures. Another difficult part is that in the IR, we are missing explicit constructs that are useful to our programming model. And they are currently substituted with metadata and intrinsics. However, it's very ad hoc and not a standard way to do it, not an elegant way to do. The first implementation of OpenCL in Clang was version 1.1 and 1.2, and it mainly affected parser and codegen, as we had to add new keywords and new constructs that are now have to be parsed. We are using IST structure just as it is for C, but obviously we have new nodes that will appear in IST, for example, representing new types. On the codegen side, we need to accept these new IST nodes, and we have to generate code for these nodes. Also, we have to modify standard C code generation sometimes, because there are some parts there OpenCL has different semantic to C, although syntactic constructs are exactly the same. Again, we are using an IR structure as it is. We have just really very few OpenCL specific bits. For example, we are using address space cast instruction, which is something you will not find if you compile just C. Also, we have added some important diagnostic, but a lot of them are missing or were missing for initial implementations. And the test coverage is unfortunately not as good as we would like it to be. In OpenCL 2.0, we have a number of key features that are built on top of previous standards, and they basically improve different things. For example, we have a possibility to dynamically create work and the device, which is being called hierarchical or dynamic parallelism. And we are using Objective-C blocks for this feature. Another thing which was improved, as I initially told, that we have address spaces to specify where in memory objects are located. And that is a little bit tricky sometimes, because when you write your code, you always have to think of every object, every variable, where in memory it will be located. To simplify this, there is a certain way to basically write code generically and then use late binding to bind algorithms or objects used in these algorithms to specific address space or specific memory. We have several means to simplify communications, making them more efficient between kernels. For example, we can use program scope variables, which are very similar to global variables in C. Or we have pipes that are just standard streaming pattern like communications. We have inherited C11 Atomics in OpenCL 2.0 with special memory visibility scope, and we have new image types and access qualifiers. I will start introducing all of these features one by one, and I will do it chronologically the way they appear in Clang, basically. Generic address space is a way to abstract your code from memory hierarchy. In previous standard, if we had to write certain function foo that has to operate on object in different address spaces. For example, in this example, we have foo that has to take local int pointer and global int pointer. We would have to actually define foo function twice, and then we can call it with different address space objects. In OpenCL 2.0, we don't have to do this anymore. We can just say this foo function will operate on generic pointer, and later we will perform dynamic conversion between specific address space and generic address space. Address spaces are a really special thing in OpenCL because nothing is allowed on objects located in different address spaces. You can cast between them, for example, and there are very few operations that can be performed on distinct object address spaces. And because of this, it actually affected a lot Clang, so we had to change a lot of places the way the types are handled. Generic wasn't very difficult to support, however, because we inherited implementation of address spaces from previous standards, so we could just easily extend it everywhere. Just to give you an idea what kind of things it affected, so if we are to parse generic address space qualifier now, we first of all have to extend parser, of course, because it should accept generic while parsing declaration specifiers, and we are handling them as type attributes, so we could reuse a lot of existing parser code for this. Then on IST, it will appear as in qualifiers, so we will have built-in type int, and then we will have qualifier type, which will contain generic as qualifier, and then at the end we have pointer type. We had to extend, or actually we had to add a lot of missing checks for address spaces from previous standards as well, and of course extend it for OpenCL 2.0, basically disallowing a lot of cases, which makes no sense, cases that make no sense for OpenCL. In targets, it depends on the, actually it depends on the memory architecture of a target, how to interpret or how to treat generic. If there are targets that have flattened memory hierarchy, then they will map generic to some specific address space, and then there will be dynamic conversion from address space to the same address space. They're easy to eliminate. In targets where we have complex memory hierarchy, we will probably map it, or currently we map it to some unique number, and then dynamic conversion would have to be handled either by hardware or by the compiler. So some compiler backend transformations would have to be done. We had to change default address space behavior as well, because in previous standard, if you don't specify an address space of an object, it would be considered as it would have private address space. And then private address space declarations would be the same thing as not having any address space qualifier in the declaration. So these two cases, when you declare int I variable or private int I variable, would be represented in IST as the same thing, and they will just have no qualifier. Starting from OpenCL 2.0, the rules are more complex. For example, for pointer types, we have to have generic as default address space, and for scalar types, depending on whether they are global or in global scope or local scope, it will either be global or private. So because of the original scheme where we didn't have unique representation for default address space, we had to think of how to actually support it, how to support new scheme in Clang. And the way we have decided to go is to basically modify parsing of type attributes. And we could just say, if the address space type attribute is missing, we will just add it in. And we would, of course, look at the scope we are parsing and at the type which is being parsed. And then, depending on that, we will add the right address space attribute. This, however, prevented us to handle one corner case in the spec for null pointer literal, which has to be basically it has to have no address space. But currently, we are adding address space very early in the compiler, so we don't know what kind of object we are parsing yet. So one solution to that could be to add private as an explicit address space qualifier. But the problem here is they are basically affecting previous standards. And as I already told, a lot of backends are not open sourced. So we don't have any idea how much we would affect existing code. Another surprising thing here would be if you declare an object with certain type, you might see diagnostics that have slightly different type. For example, if you declare a global int variable, you might see diagnostic where the type is reported global int. That's because we are adding something implicitly in the parser. Atomic types are just standard C11 atomics, and therefore we could just map them in Clang to C11 atomics. All of the OpenCL atomics are just mapped to C11 atomics, and that is done on CMA initialization. We only have subset of types, so we could really suitably just predefine them. And we had to extend CMA with respect to atomics because some things are disallowed on these atomics in OpenCL. The good thing is we can reuse C11 built-in functions in Clang, but the bad thing is there are some things missing in Clang and also in LLVM, particularly memory scope, where you can say if your atomic operation is device-wide or if it's visible on host memory, device memory, or both of them. So this is something we have no way to represent at the moment. This can be added, but we just need to basically find the best solution to it. Program scope variables, as I have mentioned, they're just very similar to global variables in C. The difference is that their values will persist between different executions of kernels. They were disallowed in previous standards, so we just had to modify CMA to allow them. And something we had to fight with here is, in previous standards, we added implicit local workgroup storage class. For example, if you declare a variable with local address space, it would add local workgroup storage class to this declaration. And this prevented us from handling cases where we have static local, because suddenly we start having two storage classes. But in C, we can only have one. The solution here was to remove local workgroup storage class and to substitute it by checking an address space qualifier. And that actually worked everywhere in Clang, so we didn't really find out why it was added initially. Pipe is another way to improve communication between kernels, and this is standard streaming pattern where you have producer and consumer. Producer is writing data into pipe, consumer is reading data. And this is an OpenCL application, how you can basically write your code using pipe. So you have a kernel which is producer, it takes write-only pipe, and then it writes into it. And you will have another kernel which is consumer. It takes read-only pipe and reads from it. And on the host side, we will have to create the pipe, and we have to specify the connection between kernels. The pipe type in Clang, so we had to allow pipe as type specifier. Of course, again, we had to extend parser. In IST, it will appear as a new special type, which is pipe type, and it will have an element type in it. In this case, it's a built-in type. And again, we had to add a number of restrictions on how they can be used. We codegen pipe to OPEC pointer at the end. We found that there was quite some code repetition in Clang wrapper style types and also in their factory creation code in IST context. And we hope we can contribute some refactoring to that. The pipe built-in functions are defined in this way. For example, we have here int read pipe, and it takes read-only pipe object of gen type and a pointer to gen type. So gen type here is any built-in type or user-defined type. So at the end, we have some kind of generic programming style behavior to support in C99. Of course, we can't enable, or it's not easy to enable a generic programming from C++. So what we have decided to do is just to implement all of the pipe built-ins as Clang built-in function with custom check. And that allows us to diagnose them in any suitable way we need it. And we codegen it using OPEC type and avoid pointer type. Images are special Clang types. They are all handled in exactly the same way. And there is a lot of code repetition there that we are trying to get rid of these days. In OpenCL, in early OpenCL standards, we had 6 different image types, and we are adding 6 new types in OpenCL 2.0. We also have new access qualifier, which is read-write, in addition to read-only and write-only from previous standards. Again, access qualifiers are a really special thing in OpenCL because together with image type, they form unique type. So image type doesn't actually exist in language without an access qualifier. Every image has to be qualified. Again, here we inherited some problematic implementation because in previous standards, when we implemented images, we completely discarded image access qualifier. So it was parsed, and after that, it was just completely ignored, and it never appeared in IST or in IR. And of course, because of that, we had we were accepting illegal code. For example, if we are declaring write function, that should take write-only image type, and then we call it with read-only image. This is just accepted. And then we generate a call where, again, we don't have any access qualifier in IR. However, this code was still OK if you don't have a wrong OpenCL code. If you are trying to pass write-only image to write function, it will just work correctly. In OpenCL 2.0, we need to take different paths for write depending on whether it's read-only image or read-write image. And this is no longer possible with this code generation. So that's something we have to improve still, and there is currently a review set up for this to clean up. Device-side enqueue is enabled by calling enqueue kernel built-in function in the OpenCL code, and it takes block as an argument, and block basically specifies the new work which device will do. And this block just has standard Objective-C syntax with one restriction that it can have any number of local void pointer arguments. And as you can see here, we kind of have variadic prototype, but not exactly, because the type of argument is restricted to be local void pointer. So we don't see any standard compilation mechanism we can use in Clang. And for now, we are thinking to implement it as Clang built-in function with custom check as well. There are some miscellaneous features we had to add. For example, loop unroll hint. This is just very similar to pragmacy loop hint that is already available in Clang. We have no shared virtual memory attribute, and we haven't found any good use of it, so it's just currently just really ignored. And we are fixing a lot of address space issues still in CodeGen and SEMA as well. We had some restrictions to Objective-C blocks. For example, in OpenCL, we are not allowed to have variadic arguments. So at the end, generic address space is fully supported, program scope variables. We have a number of small issues to address in default address space images and atomics, as I have presented it earlier. And we are still planning to contribute with device IdleQ. Also, we plan to improve tests and diagnostic for previous standards, because OpenCL is actually derived from previous standards, so it's essential. Sorry, OpenCL 2.0 is derived from previous standards, so it's essential to improve previous standards as well. And there are some places where we can do some refactoring work as well. Overall, we made good progress on OpenCL 2.0, and we are hoping to complete in the next release. We do see it beneficial to derive from production quality C front end. We can reuse a lot of things. Although we find sometimes we really have difficulties because Clang just was not designed in a way we need to use it in OpenCL sometimes. We are trying to use to find best use of existing C and OpenCL functionality, but of course we would not accept to regress on the old standards if we need to implement some new feature. Also, we find that Clang and frontend in general is well suited these days for OpenCL, but we are missing a lot in IR and on backend side. And here is something we would like to address with the community, whether it would make sense to extend LLVM IR and make it more suitable for these kind of programming models, or we should improve support for alternative intermediate representations, such as PRV, for example. I would like to take this chance to introduce contributors as well. We are from different institutions, as you can see. Most of us are part of Kronos. And thanks. If you have any questions, please ask.
So, are there any questions? I mean, you know the drill, the microphone's over there.
Yeah, I have a observation and a question. For our out-of-tree targets, for the last couple of years, we've had support for targeting a non-zero address space for everything that is not explicitly qualified. So we possibly have some patches that we can share with you if you're having issues with that. There were lots of places in Clang where it does assume a zero address space,
yes.
And I imagine you fixed many of them.
Yes, we are upstreaming a lot of things related to address space. Actually, we always did, and that's what I actually meant with this item here.
It looks like
still fixing address space issues, and that's, I think, what you referred to.
Yeah, we have quite a lot of fixes for those, but we may have only fixed things that you've already fixed, but we can share some patches.
Yeah, that would be nice.
Useful.
Sure.
On the extending LLVM-IR or SPIRV front, there was some discussion when the Swift front end was open sourced about whether it would make sense to have a C IR that was higher level than LLVM-IR and could be used to do data flow analyses and all of the things that the sanitizers do, and then lowered later to LLVM-IR. Do you think that something like that would help you?
I think it's also similar to another discussion we had, whether we should support SPIRV and then go from it to LLVM-IR, because it's also like slightly higher level. I think it might be, it's definitely a solution. We definitely need some solution. But we also see it might be better to actually have just something like SPIRV and directly generate front-end SPIRV and then SPIRV to back-end, because it has so much information, and then you go to lower level like LLVM-IR, you lose it, and then you start closing up of missing construct with emitting metadata and built-in function, and everyone does, sorry, intrinsics, and everyone does it in different way. So it would be an interesting discussion, actually. So maybe we could take it offline.
We also have some people in our department who have been working on formal models for C. We have a PLDI paper coming up in a few months. For that work, we have a set of semantic constructs that give you the core C11 language. So we can possibly feed something useful into that discussion.
Yeah, it would be nice to follow up, I think. Sounds good.
Hi, could you comment on whether Mali GPU devices will be supported in the next release?
Are you talking about open source?
Well, by whatever means.
Because we do support them, but they're not open source.
Yeah, I know, but I mean, will they be released? Will OpenCL 2.0 drivers be released for Mali GPUs and available to the general public at large? In the next
you mean on Mali developer page?
Yeah.
I can't comment on that at this point.
All right. Right, thanks very much.
Any more questions?
One of the things you're saying there is you don't have any experience of out-of-tree implementations for this, and that you'd like to get data from it, from the out-of-tree implementations. What would be involved with for an out-of-tree developer such as myself to actually liaise with the OpenCL front-end work that you're doing in order to enhance IR and in order to discover whether or not there are issues for out-of-tree implementations?
What implementations do you refer to?
We have our own processor at Movidius, and we have an OpenCL implementation that we're building on it. But it's independent of this work.
All right.
And it will be interesting to see how we could align our implementation. But when you're giving your presentation there, you say that there's one of the problems is you don't know what the effects of your changes will be on other targets because of their out-of-tree. So while I can't give my sources into the mainstream yet, it may still be possible to liaise and do discovery to find out what weaknesses are or what issues arise from the work that's been done on OpenCL 2 in Clang, and therefore be able to improve its quality and also enhance the probability it works with other targets. And having guidance for that or some information would be very useful.
Actually, in a way, it's also similar to us and the way our companies work, because a lot of us, we don't open source backend. And then the way we do it, we try to propose some implementation, let's say in CodeGen for Clang, and then several people would look into it from different companies, and then we try to basically feedback whether we think it can create problems for anyone. And we are very open to feedback, even for existing things or things that already existed for a long time in Clang. If you feel it's not suitable for some architectures, just let us know. And you don't have to disclose any details, so we can try to be flexible.
Yeah, exactly. Thank you.
Anyone else? I think that's a no. Let's thank our speaker again.
Thank you.